All right, so this is the compute, right? We just talked about add stuff, right? Add 1. Now let's look at the interaction with the data memory. We just talked about this expression, right? We keep referring to this expression. Okay. Each one, right? Each addition can be done in a cycle, but assuming that we have a 1 gigahertz processor, let me ask you guys a question. 1 gigahertz CPU. Of course, ALU, right, can run at 1 gigahertz, right? So that's determined by the longest path of this control logic. 1 gigahertz, how many additions can we perform in 1 second with a 1 gigahertz processor? Very good. Very good. A billion, right? We can actually do a billion ops in 1 cycle. That's why we use CPUs, right? We use microprocessors to crunch numbers because they're so fast. Okay, now that you guys can probably tell, with we actually need to execute 1 billion instructions per cycle, and we can actually execute a lot of expressions, right? Compute a lot of expressions like this in just a single second. So that's where it means that it's going to produce a lot of intermediate results, right? We may have like up to 1 billion intermediate results. Do we want to put these intermediate results in the RF using flip-flops, using registers? Is that a good idea? Maybe not, right? Because these flip-flops, we just talk about the analogy, right? These flip-flops are like or registers are like the houses, right? They are expensive. They're not that compact. If you have this much of data, we actually want to put them in a more compact memory, more dense memory, like a RAM, like this, right? So that's where we actually need to shuffle the data back and forth between the RF and the main memory. Okay. First, we do want to read, right? For each compute, right, we do want to read from the RF directly because it's much faster to access the RF. But eventually, we need to, we will run out of space in RF, right? We only have usually in a modern processor, we have 32 registers up to maybe 128. Right? In some cases, we have a slightly larger register file, but that's it. Okay, we do need to move data to the RAM memory, and we also need to bring some data from the memory to RF. Okay. All right. So Ambrose is asking a very good question. So okay, so very good question. So wouldn't placing the memory in RAM make the access rate slower? Very good question. Yes. So this is something that we are gonna address, right? For now, let's just focus on this abstract diagram. Let's forget about timing right now. We're gonna talk about this in a later lecture. But excellent question. Right. So this is also the reason that we do want to interact with RF, right, as much as we can. Okay, meaning that just want to repeat, right, what I just said. Most data are actually held in this main memory because we have more space. We don't have that much space in RF. We do need to move data back and forth between the register file and the main memory. In some cases, we need to move it out, right, just to make room for other intermediate results, other data. In some other cases, we actually want to move it to a permanent storage, like a disk, like this hard drive. That's where we also need to go through the main memory. That's going to be covered by another lecture. All right. So how exactly do we read and write, right? How exactly do we access memory? So that's where we need to define some additional instructions. And this is a really important slide. Okay, this is the load and the next slide. So make sure you guys ask questions in case you don't follow. Right? First, let's talk about how to read from the memory. It's called load. Excuse me. It's called load. Okay. It means we want to load some data and then put it in the RF. Right, similar to this, right? LD means load. And this is the format of the instruction. Okay, over here. Since we want to load something from the memory, we actually need to define an address, right? We need to provide an address. Okay, this is where we want to, set address, right? M means main memory. Okay, this one means main memory. And in our 2300 processor, we're going to assume a specific format for providing or for specifying this address. Okay, so this address will have two parts. One is called base address and plus an offset, the two parts. And this is specified by this one, okay, by this term. The one in the parentheses, okay, this one specifies the base address, and the offset is specified by an immediate, okay, a constant, this offset. And we add them up. We add the base and offset to form the complete address. Right? In this case, we are reading, so this specified address, okay, where we want to load the data from in the main memory. We find that we provide an address, and then we load the data from that corresponding location, and we put the value to R3, to the register file. That's the meaning of this load instruction. And this is the corresponding pseudocode. Okay. Over here, we treat this a whole memory, right, as a giant array, okay, a big array. Okay, that's an abstract view. Right? And this is the index to the array, which is the complete address. Right? This is the address. And we read it, we put it to R3. Okay, so we have two parts, right? To give you guys some intuition, again, this is very much related to how we write software programs, right? So that's why we have this design, this kind of specific instructions. And there are actually some different ways of addressing in a more complete, more complex microprocessor. But in our case, we have this base plus offset scheme. Okay. Again, in the software program, in many cases you have arrays, right? You may have, you may access the array like this, right? You want to access the first element and the second element array. Okay. And actually, all these arrays are stored in main memory. And basic A, eventually, this symbol will be translated to a base address. And this constant, this index, will be translated to a offset. Okay, and then we add them up. So that's how we get the complete address. Right, but for now, let's just remember this is something that we need to memorize. Okay, so we have base address and offset that form the complete address. There's some more questions. Comment this. Does R1 plus 4 correspond to? Good question. Right, so this is determined by of course, the address range, right? Also the word size. Over here, let's say R1 is 16 bits. So we have 16-bit value in the register file. So then R1 plus 4. So we also have 16-bit. Okay, for this specific example. And Lauren's asking, is the base where you currently are in the register, or would it be always a set register like R1? Yes, good question. Right. Again, we assume that, right, R1. So basically, with the base address, so we assume that's already stored in a specific register. We need to read out value from that register to get the base address, and we do the plus offset. Okay, right. So R1 plus 4 is, for now, that's just 16 bits. Again, in modern processors, we may have 32-bit address or 64. Okay, and for, so what are you asking, Alma? What do you mean the fourth bit of R1 is the last? So basically, we need to do this sign extension, right? When we add things, when we add the immediate value, we need to sign extend the constant to 16 bits before we add. Does that answer your question?
Oh, I guess what I'm kind of confused about is R1 plus 4 another address in memory, or is it like an operation you're doing to whatever's stored in R1 and then you're loading that into R3 and like? Oh,
okay. Yeah. I see. Okay, let me complete the discussion here, right? Hopefully this will be more clear. Okay, I'll answer some of the questions later. Let me finish this the slide. First, right? So we already talked about base, right? Offset, we need to calculate address, right? But how exactly do we calculate this address? Right? We have base and offset. We can actually just use ALU. Right? ALU can do add, right? So that's where we use ALU to compute the address. Right? So basically, first we want to form the address, by adding up the base and offset, right? So that's the first step. And the offset is stored in the immediate, right? In this immediate field. We will talk about how we get this value, but for now, just consider this as something that just available to us, right away. Immediate value, and this one, since this is usually short, right, has a shorter bit width, smaller bit width. So when the sign extended, this immediate value can be a negative value. We can also do R1 -4. Okay, this is fine. We sign extended and we add with the register value, right? We can grab R1, the value R1 using data A, this port. That's how we get the address. Okay? And we do addition and we get the complete address here. Okay, this is R1 plus. So just to be more precise, this is really R1, right? The value of R1 plus 4. That's the address. Then we use this address to basically locate the specific element in the memory, and we read it out. Okay, and we send it back to the register file. That's the second step. We read data, then we place it in R3. So we are writing to R3. This is this is 1, right? We can write to R3. Okay, so let me ask you guys some questions quickly first. Just want to make sure that you guys follow what's going on. Let's erase this. You want to read from the main memory? Okay. First, let's don't worry too much about this. This means memory write. When we read, we set it to 0. Okay. This is also like a writing label. MD. So you want to read from the memory. What should we set this value to? This is really the marks for controlling the destination. We take 1, right? We take the output from the RAM. We set it to 1. Okay. And what is? Let's look at other signals. MB. What is MB? Okay. Make sure you guys try to follow what's going on here. Right. There will be a quiz at the end. 1, right? Because we want to add the immediate value, right? So we want to take this pass. MB is 1. How about LD? 0, 1. LD 1, because we want to write to R3. So that's where our DR is 1, 1, right? Okay. And see here, we do want R1 to show up here, right? Because we want to do R1 plus 4. 4 is here. So what is SA? SA is what? 0, 1. Very good. Okay. SB. SB. X. Okay. Very good. Any more questions? I think there was one question somewhere. Is IMM, Amanda's asking, is IMM the offset of the index then? Amanda, what do you mean by the index? The index of what? Can you clarify? Okay, not sure whether you can hear me, Amanda. Maybe you're muted. So the offset, yes, I think you asked a question, right? This IMM is basically we use this IMM to form the complete address, right? And this complete address indeed is sort of an index, right? But this is an index to the main memory. Right? We want to form this complete address. What are the MD and MW again? So these are the marked signals, right? Just look at the MW. This is the marked signal, right? Where we want to take either this pass. This is the ALU pass. Right? We want to take the ALU result, or we want to take the RAM pass. Right? We want to take the RAM result. So we want to take you want to load from the RAM. Right? We set it to 1. MW, we are going to define this, right? I'll show the complete definition. This is over here 0. This means memory write. Okay. All right. Does the data is stored in the RAM, Steve? If that's what you're asking, we do need the data from the RAM. This is the data, right? This is the data that we want to grab from the RAM. Yes, that's like the, right? So we basically want to set. We want to connect this to the DIN value, right? We want to write it to the register file. Okay. Right, so this is load. And here we want to store, right? This is also related to what Amber was just asking, right? You want to write the main memory. What do we do? So here's the instruction format. We also have this same format for the address, base plus the offset. Okay, so this is a complete address. And this is the value. We actually want to write the value of certain register to this specific location. Okay, since the offset is 0 here, so basically we are just writing to this specific location in the memory. Okay, we're going to update. So this is the address again. We're going to update this memory location with the value of R2. This is the meaning of the store instruction. Okay, store is the memory write. With the store, same thing, and we also want to form the memory address by using ALU, right, to add up the address, the base address in the register, and the immediate offset. Right, so that's the first step. Okay, and we just write it. That's it. Okay, so maybe I can just ask you guys the questions. Does data? Oh, there are some additional questions. If you want to write store, that's already answered. Amanda asking, does data in only matters when MW is 1? Let me try to address this question. Okay, first, we are storing, right? We are writing to the memory. So that's where we want to set this value, this signal to 1. Okay. MW is 1. That means this is memory write. This is basically like the write enable for the RAM. Okay. So since we are writing, we are writing to memory over here. We are not really writing to the RF anymore. So what should be LD? LD should be 0. Okay. So this is not like the low, right? So this is where we write a register value to a specific address in the main memory. Very good. How about SA? SA. Which one do we use? We want to still form the address, right? Is it 1 0 or 0 0? See here, we want to use this ALU to get the address. So that's where we need R0 here, right? And the immediate value is 0 here. If we want R0 here, so this is a 0 0. Okay. Before we talk about SB, what about DR? What is DR? Do we write to the register file? No, right? We already know LD is 0. We don't write to the register file. So this is X. Okay. What is SB? This is where we want to take this pass, right? See here? So this is also related to one of the earlier questions, right? Does data in only matter? Yes, data in only matters when MW is 1. Okay. And this is where data in matters for RAM. If we want this one to be R2, right? So we put 1 0 here. One last control signal. Oh, actually, there's one. This one is 1, right? We want to take the immediate value. But what about this one? MD. What is MD? Is it 0 or 1 or what? 1? Doesn't matter, right? Okay. Doesn't really matter. Whether 0 or 1, doesn't matter, just X, because we are not writing to the RF. These paths, right? This path is not too useful in this case. We only write to the RAM. All right, any more questions? Can you do both at the same time? In our microprocessor, no. We can only write to, in our microprocessor, we can only write to either RF or RAM. Okay, why is, Marco is asking, why is MB 1? Okay, oh, you're asking about this one. Okay, what is the 1? Because we have 0 here, right? We have offset. We want to complete the address. We want to do this one doing R0 plus 0, right? So that's where we want to take this pass. We want 0 to show up here, and this R0. That's where we have a 1 for MB. The pass is for when we are doing multiple operations, right? Like, which pass? What's the that pass?
Oh,
What do you mean by that pass?
I mean the path that you just highlighted that you said MD is X because it doesn't matter.
Right. So one thing is, we can this AL, right? So the ALU can only handle one operation at a time, right? So that's where for this expression that I used, right? A plus B, B minus A plus 1. So we actually need multi-cycle. We need multiple clock cycles to complete this expression. Okay. So that's why we need to write intermediate result to the RF. We can only do one operation at a time.
Yeah, that was kind of my question. So is that path when you're doing the expression that requires multiple cycles, like you need this path for when you need to keep writing in the intermediate data?
Maybe I can address this question later. Let's maybe move on. Is that fine?
Yeah, that's fine.
Sure. Maybe I can also address it offline. But this is a good question though. Okay, so we just talk about the store, right? And make sure you guys check these control signals offline, right, after class. And this is actually an important lecture, so I may need a few extra minutes, okay, just to complete the next 2 slides. Many of you have been asking this great question, right? So where are these control signals, right? How are these generated? So far, we have been assuming that these control signals, right, MB, MD, they just magically show up, right, with the right value at the right place. And in fact, we actually need some actual hardware called CU or control unit that generates a sequence of so-called control words. I'm going to define what exactly what I mean by control words. So these are basic signals that we have already seen. Okay, and the CU may be actually affected by the output of the ALU, not just the data output. And next time we may see that whether there's overflow or not, or carry out, may also affect the condition and the output of the control unit. Right, so this is where we do need a control unit. And we're going to use this one, this abstract, right, the black box CU, to indicate that we do have a separate piece of hardware that generates these signals, MB, MW, MD, and such. Okay. All right, and also IM. And this is the control word. So basically, this is the bundle of the control signals that we have already seen. Okay. Just want to remind you, this 3, DRSA, SB, these are the register addresses. IM is the immediate value. Right? MB is the select, right? Where we want to select either the data B or the immediate value. FS is this, just the opcode for the ALU. MD is where we take the path, right? We either take the ALU path, ALU output, or the memory output. And LD is the write enable for the register file. And MW is the write enable for the RAM, the data RAM. Right? Okay, so let's talk about another example in the just the last few minutes. Over here, I'm assuming now I'm assuming I have 8 registers in my RF. Let's go through a few more examples. I may ask you guys to do a quiz, maybe not today, in the next lecture. Okay. But there is a bonus question at the end. So first, let's look at this instruction again. Right, there's a simple addition. You know, hopefully you guys are already familiar with this. Right. This is the corresponding control word, right? Since this is a ALU, this is really an ALU instruction. Right? We do need both SA and SB. Right? We need to specify R0, R1. So that's how we assume that we have 8 registers. That's why we have 3 bits for each register address. Okay, hopefully this is not too surprising. Right? All of this should be fairly straightforward to you guys. Right? And we do want to take MB, we do want to take this pass, right? In this case, MB should be 0. Okay, let's quickly look at the next one. The next one is more interesting. What is the next one? Next one is a load, right? Is a load. We want to load from this specific address, R2. So for this instruction, tell me what is DR? Let's just go through this one by one. DR. 001, very good. Right, we are writing to R1. SA. SA. What do we want to put over here? We need to form the address, right? This is a load. Okay, 0, 1, 0, very good. R2, we want R2 to show up here. SB. Is it 0, 0, 0? Very good, don't care. Okay, because we need to take this pass, right? We want to take this pass to form the address. That's that. What is IMM? What's the immediate value? 0, right? This is really R2. This is really R2 plus 0. How about MB? MB is a 1 because we want to take this pass. 1. FS is just add, right? We want to add to the addition over here to form the address. MD. This is a load, right? We do need to take this pass to write to the register file. So this is a 1. LD, also 1. MW, 0. Okay, we are not writing. Very good. Okay. All right. Okay, here's the bonus question. Let me show you. Here's a bonus question. Forget about this one. What exactly is going on here? What's this? I'll give you guys the whole class a few seconds to read the control words and wait for my signal. Right? Don't enter anything in the chat window. Wait for my signal. My question really here is, right, given the control word on the right, can you guys tell me what's the corresponding instruction? I'll start the countdown now. I'll let you guys know when to raise hand. All right, please go for it. If you have an answer, raise your hand. Lauren, go ahead, since you already entered something in the chat window.
I said add like register to nothing, like add to register 0 and don't store it.
What kind of instruction are we talking about? You're very close. I can almost give you the full credit. What exactly is the instruction?
Load?
Okay. All right, I think you're very close, Lauren, very good. But let me give another student a chance. Steve, I think you're the next.
Yeah, we're essentially doing the procedure that Lauren described, but then we're writing it into the RAM.
Right, but what exactly is the instruction? There's a name for the instruction.
Store, we're storing.
Very good. Okay, store. Right, Lauren, I'll also give the credit. Okay. You are almost there, right? This is actually store. Do you guys agree? What is the, tell me like which register are we reading? Just one more minute, but before we conclude. Which register are we reading from? Feel free to put in the chat window. R2. Okay. Is that the address or the value that we need to put into the memory? R2. Okay, first, just in case you guys missed this, right? So this is store, right? Memory write is a 1. This is store. This is really important. So later on in the homework and also in the exam, pay attention to this one. MW is 1. This is store. That means we are writing to the memory. Okay. And then the rest is not that important, right? So all that is important is what is SA and SB. Okay. So SA is the one that we put over here, right? For the address. So this is R2. Okay. So basically we have this degree. And sorry, I write it in the opposite way. And we want data B to be R0. Okay. This is the complete instruction. Any questions? Okay, if not, we are done here. Sorry that it took me a few more minutes, but this is a really important lecture. So I do want to address most of the questions. Okay. And we'll do a quiz in the next lecture.